We're doing 6033 in the news time. I had like 3 different things that I could have talked about in this new segment today. Today we're going to talk about the vaccine website in Massachusetts and how drastically it failed. So last week in Massachusetts, people 65 and older started to be able to get the vaccine along with some other groups of people, but this is like 1 million more people getting the vaccine. And a lot of the websites to go make vaccine appointments crashed. So you can see 2 quotes here, one talking about how the system did not scale fast enough, and another talking about one of the websites that used a cloud computing service to scale up server power to meet demand, right? So since this is happening in the news right now, we're not in a place in 6033 yet where we can talk about really the technical details here. We're on lecture 2, so it's going to be a minute. But I want to present you with some questions so that as you start to see things happen in the world for the next couple of weeks, you could just start to think about like how 6033 is involved. So there are a couple of just basic technical questions. Why would this have been, right? Why didn't the state's website scale to meet demand? How might they have tested for that? How do we understand how our systems scale? And in what dimensions? There are lots of ways you can talk about scaling. There are the number of users you can handle, the number of requests, the amount of data, and those things tend to be correlated, but you can think of scale in many different axes. And then some more interesting questions in my mind. Companies like Amazon and Google provide these sort of cloud computing services. Are they the only places to get that, right? And why might that be? And what implications would that have? So in particular, in the context of vaccines, what are the consequences of having public infrastructure that relies on private companies to work, right? So these are just questions that I'm putting in your minds. We are going to talk about all of this stuff as we get through the class. We'll talk about how to build things that scale. But again, it's happening right now. So I wanted to talk to you about it right now. Other exciting things that are happening right now. We went to Mars. That's very cool. We'll talk about that on Wednesday or next Monday, depending on when I get to it in this new 6033 in the news segment. Okay, so lecture time. Today, we are going to talk about naming, all right? So how are we getting here? All right, last time we talked about complexity. We talked about how it limits what we can build. One of the goals of system design is to limit complexity. And one of the ways that we do that is via enforced modularity, all right? Some external mechanism is preventing errors from propagating between the modules. And you've seen one example of enforced modularity right now, right? You've seen this client server model. And there, the mechanism that is enforcing the modularity is a physical separation between these 2 modules. Okay, the client and the server are literally on 2 separate machines. What we're going to focus on today is a problem which I kind of totally ignored last week, intentionally ignored, which is that for the client and the server to interact, really for any modules to interact, they need to know each other's names, right? So for instance, for the client to make this request, it needs to know the name of the website, right? And in fact, it needs to know this entire URL, right? We can't buy our llama if we don't know the webpage where we go to do that, right? And so this is what we're going to talk about today. Naming on the internet is a common example. So thinking about like how this host name gets formed, how this URL is formed, and what that means. Super common example. In fact, we're going to study it in depth later today and in tomorrow's recitation. But naming as a concept is pervasive in all of computer systems, right? The exact details are different, but there are commonalities. And so for the first part of today's lecture, we're going to focus on kind of those commonalities. Like we're going to talk about naming as a high level, kind of more general concept. And in the second part of today's lecture, we're going to return to the issue of names on the internet. We're going to do a case study looking at DNS, which is a domain name system. I will get you kind of started on that case study today. You'll talk way more about DNS tomorrow in recitation. It's a great example to start early with. It's going to be one of our first looks into how the system was designed and sort of why it was designed that way and pros and cons of this design. We could talk about DNS forever. We'll come back to it repeatedly in the class, right? So we're talking about names. And rather than start you out with a definition of like what is a name, I think it's actually useful to start with some examples. All right, so I've given you some examples here. KWS.com, that is a name. This URL, that's a name. You can put it in the chat. What are some other things that have names, or like what are some other names? You can think of them in the context of computers, or you can think of them in the context of world. Just tell me some things that are names. Yeah, variables have names. Awesome. Right? Even here, like URL, HTML reply, those are all names. Names are names. Yes. Oh, llamas do have names. Classes have names for sure. API calls, functions, all of these things. Someone said phone numbers up in the chat. All good. Okay, some other suggestions. So here are some that I came up with prepared earlier on this post-it note. Okay, here are just a bunch of things that have names, right? MIT.edu is a name. My email address is a name. My Kerberos username. This might be like an x86 processor register. It has a name. Functions, classes, IP addresses, URLs. All right, there are names everywhere. Right? So what exactly is this? All right, what is a name? Well, you've probably thought about this in the context of software. Right? You could think about creating a copy of an object and passing that copy around, or by using a reference to the object, right? Passing it by name. Same thing applies here. All right, you've probably seen it in software engineering, happens everywhere in systems. Right? So the first question is just like, what do we get from names? Why do we use names? So I want to tease that apart a little bit. We're going to stick with the same example. We don't need to really worry about the requests and replies getting dropped. So it's fine to just think of your client and server looking like this. All right, so why use names? In general, they help us achieve modularity. They provide communication between modules, which lets us organize things into modules. But they also provide a number of other properties, or can provide a number of other properties depending on how we design them. So I'm going to start with 4 properties. I don't want to say that they are obvious uses of names, but there are 4 properties that, even if you've never thought about them before, mirror how we use names in the world, not just in computer systems. All right, so we'll go through these 4 first, and then we'll get to some more kind of subtle properties about names. So the first is just retrieval. Names let components or modules of a system retrieve objects, right? This client is able to retrieve the Llama page because it knows the name of the Llama, right? Depending on our system, retrieving something with its name might let us perform some other actions. For instance, you might have if you have a file system, you have 2 different names and the absolute path name, they're exactly the same. You know that they point to the exact same file. All right, so you sometimes can do some additional things here. Related to, or at least I think related to retrieval, the idea of sharing. Multiple modules or users can name a shared object, which means that lots of clients here can look at that Llama page. We could even be in a system where these clients are taking actions, right? Like maybe instead of coming after Amazon, we're going after eBay. And so multiple clients are bidding on the same, they're bidding on the same Llama. All right. You can even do more than just access here, right? You can do manipulation. If you're, again, thinking about this in the world of software, if you're passing things by name, a receiving function can manipulate the object. Sometimes you want that, sometimes you don't. Right? That's something that you would decide as you're kind of figuring out how names are going to work in your system, but it's certainly something that names can let you do. All right, so retrieval, sharing. Third thing, user friendliness, right? KWS.com is easier to remember than, say, a particular IP address, right? Although interestingly, KWS.com and that IP address are both names, right? So there's a little bit of layered naming here. We're going to talk about that a lot more today. The variable name HTML is easier to remember than a particular location in memory. A file name is easier to remember than some memory address. Right? So user-friendly IDs. And then one of the last things, yeah, IP internet address is fine. Yeah, we'll talk a lot more about IP addresses later today because we're going to spend a lot of time mapping host names to IP addresses. All right, so we'll talk about exactly what that means in about 15 minutes. All right, and then the last thing that not all names can do, but some names can do, is in fact related to this, right? Addressing. So some names also specify locations. So this address that I've given you right here, 18.25.4.171, right? We're not going to talk so much about how that is constructed in this lecture, right? But this address is something that the infrastructure of the internet understands. The infrastructure of all networks understands. And it can look at a piece of data that's intended to go to this address, and it knows what to do with that, right? Just like if I gave you the address, 77 Mass Ave, room 3846, you could plug that into like Google Maps, you could drive to MIT, and you could show up at my office, right? But without that information, if I just said Katrina's office, that's not enough for you, right? So names let us, when we want to do some addressing. And so again, I've collected these 4 properties together because even though we see them in computer systems, you often see them in the world. The next 2 are a little bit more specific to systems. And so for this, I'm going to stick with the server, but I kind of wanted us, we don't really need the client for this example. And I'd like to think of there as being a file on this machine. It's just nice to be able to talk about a file. So this is the file that our server is storing a lot of information about the llama. The price of the llama, its size, its color, right? Like you could think of it as a spreadsheet, that's fine. We don't really need the internal details here, all right? So what else might we be able to do here, all right? The first is hiding, right? So as I've said, names are going to help us achieve modularity. And as part of the modular design, names let our systems hide implementation details, right? So in a file system, like the one I've showed you here, I can name a file without having to worry about how the file system's memory is laid out, or worried about exactly where llamadata.txt lives on disk. I can just use the name, and then the operating system will take care of getting me the actual contents of the file, right? That's a whole process in and of itself. You'll talk more about that on Thursday for a particular operating system. But the name lets me not have to worry about that. You can do another type of hiding with names as well. In some cases, you could even do a form of access control. So access control just, literally means controlling who or kind of what components of the system have access to a particular object. All right. So for example, if you've used Google Docs before, there's, you can share a Google Doc with a particular user, or you can get that link, right? And if anybody has the link, they can view the file, but the link is like really long and it looks pretty random, right? And so the intent there is that, well, that's so long and so random that no one's just going to guess it, right? No one's going to happen upon your file. So that's a form of access control via naming, right? So here's hiding. And then related to hiding, or related to this example at least, we have a form of indirection. All right, so in this particular case, I talked about how nice it is to have the name of the file, not have to worry about where the file lives on disk. And in fact, if the operating system, at some point decides, well, okay, I was storing llama data.txt over here and I want to move it over here, right? I want to defragment some things. I want to get memory closer together. All of that can happen, right? All of it can happen without the user being notified of it, all right? It lets sort of that backend change things without having to notify everything that worries about the name of this file. Now, this isn't desirable for every name. For instance, if we go to our llama page and we buy our llama, and before that transaction goes through, Amazon changes what the page refers to, and all of a sudden we don't get a llama, we get like a goat or something, that would be undesirable, right? But it is desirable in many cases. We'll see a prominent one later today, right? So broadly, what you're going to see today is that we can actually get certain functionality in our systems, right? Things like indirection and things by the way that we pick our names, right? The design of how we construct our names, how we kind of figure out what names map to. This is a important part of system design, right? How we design our naming scheme It should reflect the properties we want in the system of a whole, right? And sometimes the design of the naming scheme can even kind of make or break the system, right? We will see one such example today, right? So just so you can understand a little bit about what's at stake, we're going to start talking about naming schemes, right? So design of naming schemes helps it achieve these properties. So let's think about places where you have seen naming schemes. So I'm going to drag something over to this other screen real quick. All right, so, I'll make that smaller. Okay, so I have super simple Python program. It's not doing anything interesting. All right, so 3 seconds, I'm gonna start. I'm gonna sleep for 3 seconds. It's just gonna wait and then it's gonna end. And all it's gonna print out is the start and end time, right? The reason we're looking at this particular example is because it had a few different variables in it. We don't have to worry about sleeping or anything like that. All right, and so I can run it. It's gonna wait for 3 seconds. All right, and then we get this nice output with some times in it. All right, and I'm doing this because it's Python, right? It's a language that you all are familiar with, and you are probably familiar with sort of the, the naming schemes and even naming conventions in Python, right? We've got variable names, lowercase letters, underscores. Some things are not allowed to be names in Python, right? I can't do that. It's not a variable name. That's not allowed here. But let me show you an example of maybe a bad naming scheme. Like, let's say, okay, Howie's going to develop Python 4, right? We've moved beyond Python 3. He's developing Python 4. And Howie decides, okay, Python is just too friendly. And so Howie decides to implement a naming scheme where the only thing we're allowed to do is use the letter X. All right, so every variable has to be made up of some number of the letter X, right? And we can run this code. Let's see if I get this right. All right, so that's my Python in Howie's scheme. So we can't even do that. There we go. So that was unintentional, but a good example. All right, so this program, now that I have fixed that bug, is going to do the exact same thing. It's going to run just fine, right? Because underneath, Python doesn't actually care what the names are. But tell me, how do you like Howie's new proposed naming scheme? How do you like this idea of your only variable names you're allowed to use can only include the letter X? Is this good for you as programmers? Do you feel good about this? No, it's confusing. You don't like, wow, I hate it. You, yes. Yeah, it's not good. Okay, better than just underscores, but like is a low bar. Yeah, this is not great. Okay, this is not great, certainly from a usability standpoint. I mean, right, you saw I didn't even get it right on the first time and I came up with the example, right? I knew exactly what I needed to type and I still failed, okay? So yeah, that's not a good naming scheme, right? It's not a good naming scheme from the user usability. And anyone who says they like it, yeah, wait until you get like the 4th variable or something. Right, but remember, we're going to go beyond just the world of software engineering. We're going to look at systems where certain bad naming schemes, it's not just that they are hard to understand or inconvenient, they will actually prevent the system from working properly. Okay, so you've seen examples of names, right? We sort of motivated their use, and I've been talking about this idea of a naming scheme, right? So what is a naming scheme? Another way to ask this is, well, what did all of these examples have in common? Right? We've looked at a bunch. We've looked at, host names on the internet, file names, Python, all of these sort of things. All right, so here's what naming schemes have in common. They have a set of names. All right. In the example that I just gave you, in normal Python, not our X only Python, I can't start a variable name with the @ symbol. All right, that is not allowed. It is not in the namespace of Python variables. All right, so there's names. Then there are values, right? A set of possible values that the names are going to map to. You might sometimes hear people talk about the universe of values. So I've got names over here. I've got values over here. I've got to figure out a way to go between them. All right, so we will have that. It will also be a lookup algorithm that translates a name into a value. And depending on what's going on, in some cases, a name might translate to multiple values. Or a name might translate to nothing. All right, we'll see some examples of lookup algorithms today. Another word that you might start to hear, sometimes people will talk about this algorithm as a name resolution algorithm. So we'll talk about resolving a name instead of looking up a name. That's just terminology that tends to come up here, right? So let's think, let's think of another example, just so you have more things to kind of latch onto. Think about a file system. All right, our namespace might include, say, combination of ASCII symbols sort of separated by backslashes, right? I should be familiar with file names. In fact, I can give you one real quick. All right, so we can go back to the terminal that I just showed you. All right, so here's file names. Naming.py is the file that we just ran. These names can have a context, right? So for instance, in my home directory here, the name naming.py makes sense. That file is in that directory. I can look at it. All right. This file also has a full or an absolute path name, which I will remember what it is. Apparently I will not. There we go. All right, so this is the absolute path of this file. And what this tells you is that in some systems, names have a context. If you're in a particular directory in a file system, you can ask just for a file like homework.txt if it exists in that directory. But if you're somewhere else, that no longer makes sense. You want this absolute path. Okay, so that's known as the context of the algorithm. So when you are presented with a new naming scheme, the first thing to do is to try to figure out, some kind of basic things about these three things, right? And again, we're gonna do an example with DNS, but let me tell you the types of things that we think about. I'm gonna kind of present to you a bunch of questions. They will all be in the outline for this lecture, so don't worry about having to write every single one of them down, right? But when we think about the set of names or the namespace, we'll think about, okay, what is the syntax of the names? Is there any internal structure to the names? Is the namespace global or context-free or local? Like, how does context fit in? For the values, there are lots of questions, right? What are the values? Does every name have a value? Or can you have what we might call dangling names? What part of the system has the authority to bind a name to a value, right? In the file system, who gets to say what, naming.py refers to, right? Can a single name have multiple values? Does every value have a name? Can you name everything? Could a single value have multiple names, right? Are there synonyms? Can the value corresponding to a name change over time? Right? These are all things that we think about when we think about naming schemes. And then when it comes to the lookup algorithm, certainly there's just the first level question, which is how does it work? Right? And then, what context is used to resolve the names? What part of the system specifies it? Where does the resolution actually happen? Like, who does it in some sense? All right. So again, this is a very abstract view of a naming scheme. Right? It's important because, again, these naming schemes come up everywhere in systems, and it's important to think of them as, a common thing. But I do think, at this stage, yeah, you've experienced some naming schemes, you know about naming variables, you know about naming files, but this probably feels very hand wavy at this point, right? Like, what is going on here? Like, why is this interesting? I think might be a fair question from some of you. So how do we do this? How do we design these naming schemes? How do we answer all of those questions I just gave to you? Okay, so we're going to learn by doing, right? We're going to get a handle on these questions about namespaces and design trios and all that. We're going to answer them for a particular naming system, okay, for the domain name system, DNS. So we're going to let you see a naming scheme in action. It's going to let you study a system that provides the lookup algorithm. We'll see that some lookup algorithms are much more involved than others. And like I said at the beginning of this lecture, I'm going to get you started on this, but you're going to talk about it a lot more in tomorrow's recitation, right? And then on Wednesday, we're going to talk about virtual memory lecture, which is, among other things, a naming scheme for computer's memory. On Thursday, you'll talk about the Unix operating system. There will be a lot to say with respect about how Unix names things. So there's a lot of naming going on. But let's talk about DNS. DNS is very fun. I'm a big fan of talking about DNS. All right. So the job of the domain name system is to map host names, which are things like ecs.mit.edu or google.com or whitehouse.gov or other websites, right? To map those host names to IP addresses, right? So this system, someone is going to give it a host name, and that system is going to return an IP address. All right. What this is used for, in this example here, we're going to stick with this one. So looking up eeks.mit.edu. All right. If you want to go to the department website, the Eeks department website, right, the content of that website lives somewhere. All right. We need an address for where that content is. All right. And DNS is not just used for things that are viewable on the web, right? So you tend to get to any machine with a host name. All right. So before we go any further, since somebody asked about this in the chat and I promised we would get here, right? Let's talk about these addresses. Okay, these IP addresses. They're a type of name, right? It's a type of name that's used to locate an object. The way IP addresses are structured allows networks to use them to get data to particular places. So if you send a packet to an IP address, something like 18.682.1.6, all of the infrastructure, all of the routers involved, all the switches involved, all of the machines involved, it knows what to do with that packet. Just like the example that I gave you earlier in this class. If you mail a letter to 77 Mass Ave, room 38476, Cambridge MA 02139, the Postal Service knows what to do with that, right? If you put a letter in an envelope and write Katrina's office on it, the Postal Service does not know what to do with that. Even if you write Katrina Lakurtz's office on it, the Postal Service will not know what you mean, right? In the context of the internet, these IP addresses are structured and assigned in such a way that makes this possible. There's going to be like a whole week of lecture for us, how data gets to different places on the network, right? This is what you need for today. The same thing is not true about host names, right? That's the analogous thing to Katrina's office here. If you tried to send a packet or a piece of data to ecs.mit.edu, network doesn't know what to do with it, okay? So a natural question is, oh my gosh, why have host names on the internet at all? Why aren't we just operating with IP addresses, right? There are quite a few reasons. One that you'll often hear is just user friendliness, right? eeks.mit.edu is meaningful, right? Even if you've never been to the ECS department's website, you kind of know what to expect here, right? That IP address does not carry the same meaning, and you don't get to pick your IP address, right? It's assigned to you, just like you don't get to pick the address of your house, right? But there are some other subtle benefits that we can start to see by asking some of the questions that I gave you about naming schemes. So for instance, with DNS, can a single name have multiple values? Okay, could this address, eeks.mit.edu, could it map to multiple IP addresses? It can. DNS allows for that, allows a host name to map to multiple IP addresses. One of the things that you can do with this is balance the load of a web server over multiple machines, right? This isn't possible if you're only working with IP addresses. Something that various vaccine websites might have wanted to do, right? It gives you a type of load balancing. How it's done is complicated, right? That's like a whole lecture, right? But it gives you that ability. Additionally, with DNS, a single value, so like a single IP address, can have multiple names, right? What that means is, I could conceivably host multiple websites on the same machine, even if the websites were logically different, right? Another thing that you'll see we can do with DNS is the answer to the question, can the value corresponding to a name change over time? It can, right? Having this level of indirection, right, between host names and IP addresses, it lets administrators, network administrators, move around exactly what machines a host name refers to, right? So if we had eeks.mit.edu and the server is plugged into one particular place at MIT, and we want to buy a bigger server and we want to move it to a different room, it's going to get a different IP address, but the host name can stay the same. Okay, so this is a little bit about names and values. Now we need to try to understand how this is actually going to happen. What is this lookup algorithm like? All right, so we're going to go through a couple of ways it could work. All right, so let's think about a couple of things. Here's one idea. All right, lookup algorithm like version 0. Okay, so here is my computer. Here's your computer. Here's Karen's machine. Here's Hallie's machine. Okay, so we all have our machines. And you know, these machines have got to have some notion of mapping a host name to an IP address. So here's my first idea. They're just all going to keep a file. Right, here's a file that lives on these machines. And I'm only drawing 4 machines here because I don't have time to draw the whole internet. Right, we have these files. All right, so we're going to call these files host.txt. Right, and so every machine in my drawing, every machine on the internet is going to keep this file. And when it needs to do something like find the IP address of ecs.mit.edu, right, it's going to look that up, right, in its file. It's just think of it as like a table lookup, even a spreadsheet, right? Column A is the host name, column B is the IP address. Simple enough, okay? Now, let's think about what's going to happen here, right? I drew 4 machines. There are more than 4 machines on the internet. If you leave 033 with one fact, it is that there are more than 4 machines on the internet, okay? So one thing, this file is gonna get pretty big, right? But you know, maybe we all have a lot of storage. The other thing that is gonna happen here, all right, let's say here, we're all here on the internet, and then Mark joins us. Mark adds a new host name and IP address mapping into the system. I've gotta get that update on every single machine here. Right, and if an IP address changes, right, if the mapping between one name and one value changes, that update has to get to all of these machines. Okay, so we're gonna play, or we're gonna have a lot of different updates going around this system. That's going to prevent it from scaling. Also, I'm watching the chat a little bit. I will say the IP addresses that I'm using in these examples are not the actual IP addresses. We'll talk about why that is at the end of lecture. Okay, so if you're trying to actually do some hands-on stuff, that's not going to work out for you. You're going to get a lot of redirects. All right. This system, though, this is how the internet worked when it was very small, when like it was on par with this picture. It's not something that scales to the size of the network today. All right. So, okay, let's try something else. All right. One of the things we didn't like about that is just all of these updates. How do we keep these updates up to date on every machine? All right. And there are a lot of updates happening here. So let's try, instead of this scheme, we'll go with like a more centralized system. All right. So here's take 2. Take 2, we're going to buy a really powerful machine. And you can tell it's powerful because I've drawn a larger rectangle. It's going to keep this file. All right, this file lives on this very powerful server. I'm still here, you're still here, Karen's still here, Hallie's still here. All right, but this file only exists in one place. All right. Whenever an update needs to be made to it, just has to talk to this machine. Very powerful machine, very big rectangle. Okay. And every time one of these machines wants to make a request and say, hey, what is the IP address of eeks@mit.edu? Makes a request to that machine, and the machine sends a response. All right, so you'll start to see requests flying around like this. All right, so this system got a little bit easier on the delegation side. There's sort of one centralized place where we send updates, right? If I'm adding something, if I'm adding a mapping to the system, it goes to this machine, right? Up here, I had to get it to all of these machines. But you still see, we still have a lot of requests going around. They're all going to this one machine. We are still going to have issues of scale. So for DNS, we actually need to balance quite a few things. Keeping these mappings up to date, and again, they change quite frequently. Dealing with lots of requests from lots of different places, these are all issues of scale. So we're going to try a solution that has some distributed components where there's not so much one big rectangle. All right. So I am going to give you a first look of DNS in lecture, right? In DNS, there is no single table that stores all hostname to IP address mappings, right? Instead, these bindings are distributed across many different name servers. This brings us to just a different problem. How do I know which server has a particular binding, right? And that problem is solved in large part by the structure of the names themselves. So let's talk about the structure of these names. This is something that you have interacted with a lot, even though you might not ever have thought about it, right? This name, ix@mit.edu, I'm going to draw it slightly different. I'm going to draw it in a stack. All right, and then let's expand out on this. All right, ix@mit.edu, that's one host name that you might be familiar with, but there are lots of other host names that end in mit.edu. Right, there's web.mit.edu, www.mit.edu. Right, well, you know, Mickey, all sorts of things. I'm just drawing some of them here. In fact, there are other host names that end in edu, right? Berkeley.edu. And there are lots of other ways to name websites, right? To end websites. There's .com, .net, .org, .gov, all right, and all sorts of host names that go off of that, right? This is a partial view, for sure. Again, not drawing all the host names on the internet. I don't have the space for that, right? So what are we looking at here? What are we starting to think of here? Each name here corresponds to what we call a zone, right? And name servers associated with that zone keep track of the names in the zone, all right? What you can see here is the start of a hierarchical design, all right? And to make this into a nice, true hierarchy, we're also going to add a root zone at the top. We'll talk about that in a second. And so this is a partial view of the DNS hierarchy, right? And we're going to use this partial view for our example of looking things up. All right. Now, at this stage, we're really not thinking about lookups yet. We're thinking more about organization. In some ways, we're thinking about the people involved. All right. What this means is there is a name server or a set of name servers owned by MIT, like located, you know, at MIT, owned by MIT, that deals with the mappings that end in mit.edu, right? And some of that gets delegated downward, all right? There are name servers that ECS runs that deal with names that end in eeks@mit.edu. So like if I have katrina.eeks@mit.edu, we could keep going down this hierarchy, right? There are name servers that deal with things that end in edu, right? Now, it starts to get interesting and maybe a little bit harder to imagine when you start to think about things like, well, what is the root server like? What is .com like? All right. The root zone is maintained by a nonprofit corporation called ICANN. .com is maintained by a company called VeriSign, which will add a new name to the .com namespace if you pay them, right? And so again, we haven't talked about a lookup yet, but this design choice helps us think about how to keep these mappings updated, right? And how to deal with delegation. MIT worries about keeping its mappings up to date, right? It doesn't have to forward all of those updates around to other zones, right? Because they aren't in charge of them, all right? So I'm going to get you started on how this basic lookup algorithm works. You're going to continue this discussion tomorrow in recitation. And in fact, what I present to you in lecture, you should not be convinced that DNS solves the problem that we solved before. I'll point out why at the end of lecture. Oh, broccoli's on the move behind me, right? So how do we look up a name, right? How is this lookup going to work? Conceptually, we want to just walk this highway, all right? The root server is going to be able to tell us, hey, I'm not in charge of eeks@mit.edu, but I can tell you where the name servers are to get you one step closer, all right? I can get you to the name servers that deal with edu, right? edu name servers are going to say, hey, I'm not worried about eeks@mit.edu either, but I can get you the name servers that say things about mit.edu, right? And so on. All right, so let's see how this works. Here are some name servers that we're going to be involved with for this example. root name server, edu name server, MIT name server. I am simplifying things so that there's just one name server per zone. In reality, there's more than one, right, to deal with things failing. Again, we could talk about that more tomorrow. All right, so I have my name servers here, and what do they have with them? All right, this root name server is going to have a table that says, here are other name servers below me. All right, here are the name servers one level below me, for edu, for com, for .NET. All right, this NS tag at the end of that listing just stands for name server. All right, so in particular, 192.14.161.192 is the .edu name server. All right, that edu name server is going to have, right, name servers for things below it. In this example, MIT and Berkeley. In reality, right, a bunch more, right? But in this example, MIT and Berkeley. All right, looking at this, we haven't looked up yet, right? And then MIT is going to be able to tell us things about actual websites. All right, so conceptually what I want to happen is for the root name server to delegate clients down to the edu name server, which delegates down to the MIT name server, which gives us the answer. All right, so how does that actually happen? Here's you. You're a DNS client today, right? Your laptop. You're going to make some queries. All right, you're going to start by sending a query to the root server, which presents us with a problem, right? I haven't given you an IP address for the root server, right? And normally the way that you get an IP address for something is to use DNS to look it up. But that's not going to work here because you're trying to get DNS started, right? So IP addresses of root servers are hard-coded into your machines, all right? So they do not change very much. So here is the IP address of one of the root servers, all right? So your DNS client is going to send a query to that root server, all right? And the root server is going to say, I can't help you. I can't resolve eeks.mit.edu for you, but I can get you one step closer. We can get you to the name server for things that end in edu. All right. So, okay, now your DNS client makes another request to the edu name server, which says a similar thing. Hey, I can't help you, but I can delegate to you. That's the MIT name server. All right. So, okay, go ask the MIT name server, all right, which says, hey, yes, I'm the one you want. Here is the IP address that you are looking for. All right. Now, this is like a first attempt at using DNS. So I'm going to point out, though, some problems with this. Can something be a name server in the actual destination page too? Typically, the servers that are acting as name servers, I don't think are also hosting websites. But you can certainly have, like, for instance, berkeley.edu, you can put that into your browser, right? And it'll get you to a web page, right? So you could have a name server for dealing with that, and also a web page associated with that. I'm going to let also some of the staff jump in here because I know at least two of them can say a lot about DNS. They use a really big rectangle. Amazing. All right, so what's still left to deal with here? What I just set up for you is exactly like the big rectangle. I just told you that every DNS client starts by going to the root. That's the same problem we had before. All right, so there's got to be something in DNS to stop that from happening. And in fact, there is. All right, you're going to talk about a couple of really, really important, I don't even want to call them like add-ons to DNS because they're so pivotal, right? You're going to talk about other properties of DNS that let us avoid this. All right. So indeed, not every DNS query starts by going to the root server. There's this reliability issue, right? What happens when a name server fails? Okay, I told you part of the answer to that. Actually, all of these zones have multiple name servers. But then you have a question of like, well, how do we deal with consistency? How do I make sure all of the MIT name servers keep the same table? What if they don't? Is that a problem? Right. And there's also reliability on sort of the security side, right? What if things get attacked, right? This, we won't talk about security until the end of 033 in much detail. One of the big interesting and terrifying things that happens here. Often when we think about security issues, just as humans in the world, you might think about like your personal data being stolen, or like your personal machine sort of, getting like taken down or something. Imagine what happens if the infrastructure that backs the internet is attacked, right? What if all of the DNS name servers go down? Then how do we interact with things, right? It's challenging. And then there's also, a control issue. Who should own the root server? I saw some questions about things like VeriSign and things like ICANN. Who gets to be in charge of that, right? It's certainly a question, all right? So there are a lot more details about how DNS works, right? So you're going to read some of them in your textbook. You're going to talk about a lot of them in recitation tomorrow. This is not the end of DNS for you, right? So, but let's put this in the context again of kind of naming, right? So you've seen client server model, which allows us to enforce modularity. DNS is an example of that model, right? DNS clients and servers, right? So naming is what allows these modules to interact, right? DNS is a great case study for us in things like hierarchy, scalability, delegation, decentralization, lots of other things as well, client server models, caching, security, all sorts of things, right? So this is the end of naming in lecture. What you're going to see Wednesday on lecture, we're going to move away from these sort of big networked systems for a little bit. So we're going to move away from our Amazon Llama buying. We're going to move away from things like DNS, and we're going to start to focus in on, well, how does your machine work, right? And in particular, we're going to deal with this question of, so far, I've shown you one way to enforce modularity, and just put all of your modules on separate machines. This isn't going to work for us just as normal users, right? I don't want like one machine for email and one machine for Zoom and one machine for internet browsing, right? That doesn't scale, right? So job of your operating system is to try to deal with that. And so we're going to start talking on Wednesday about how that is done. You'll see naming in Wednesday as well. We'll just be applying it to a different system. All right, so again, just like I gave myself, I don't need to give myself a screen. I can just stop recording. Let's remember how to do that.